Hello students, now I am going to discuss on the topic silicon controlled rectifier. You are familiar with rectification operation. That means by using this particular symbol or a circuit, I can build a rectifier mainly. This they have specified it is a silicon, it is made up of silicon material, and they have used one term here which is controlled. This controlling is done with the help of gate. So earlier diode was having only two terminals, anode and cathode. Now it has got one more terminal which is gate here. Now looking at the behavior or characteristics of the SCR, you can see it has got two characteristics, forward characteristics and reverse characteristics. At the reverse biasing, it behaves like a normal conventional diode. There is no change in the reverse bias. Only the controlling operation happens at the forward biasing. So that means VF it should be forward biased and the anode current will be seen here. So VF or VA here will be seen at the x-axis, and at the y-axis we will see the anode current. What is this curve and how we obtain this curve? And it has got a different region to explain here. When Ig is equal to 0, you will get this curve, and it has got a different regions to explain. What are those regions? Let me highlight and explain to you. Starting with the first forward breakover voltage, which is over here, voltage which is observed at when Ig is 0. It is the voltage at which for a given Ig is 0, the SCR enters into the conduction mode. Just from here it has entered to the conduction mode. This voltage reduces as Ig increases. That's what mentioned here. When Ig is 1, the conduction mode enters at the earlier stage. Again when Ig is 2, again the conduction happens quicker. So that means when Ig is 0, the forward breakover voltage can be seen here. Now the next one is the holding current. This is the holding current. It is the value of the anode current below which SCR switches from conduction state to forward blocking region. So you can see here, especially this region depicts that it just started to the conduction, below which it enters to the blocking region, forward blocking region. That means your SCR still not on. Next, IL, latching current. It is the minimum value of the anode current required to keep SCR turned on after removing the gate signal. Latching current is larger than the holding current. That means it comes over somewhere here. So your IL is greater than the holding current, which is nothing but it is the minimum value of the anode current required to keep the SCR turned on after removing the gate signal. When once the SCR turns on, gate loses its control. Though I remove this gate control signal, but still anode is in an on state, which is conducting. So we will find this particular curve. Next, forward conduction region. So which is this? So where SCR is already turned on. It is the region in which SCR is on or short circuited and is in conduction mode. In this region, the SCR conducts forward current from anode to cathode. So it starts conducting. SCR is on already. So because of that, the current is increasing in this side. Anode current is increasing. Next, forward and reverse blocking region, where I am going to talk about these two parameters, forward and reverse blocking region. These are the regions in which the SCR is off or open circuited and no current flows from anode to cathode. So it's an off state of the SCR. Next, reverse breakdown voltage, where I'm going to talk about this here. It is the reverse anode to cathode voltage at which Zener or avalanche breakdown of the device takes place and the current rises abruptly. So this we have seen in the conventional diode also, where the reverse breakdown voltage happens maybe because of the avalanche multiplication or Zener effect. Based on the different doping concentration we have used in the material. So this is all about the VI characteristics. Now I would like to simulate the SCR. I have constructed the circuit here by using ORCAD captures here. I have built the circuit. This is a symbol SCR where it consists of, this is anode terminal, this is cathode, and this is gate, where we are going to control the turn on of the SCR. We can turn on at the earlier state by increasing the IG. So to vary the IG, we have to apply a VG, which is called gate voltage. And the voltage which is we are applying here at the this terminal, anode to cathode voltage, which is nothing but VAK, and some resistance is used in between this here 500 ohms, and at the gate terminal I am using 2 kilo ohms. When I simulate this, let's see the behavior VI characteristics of the SCR. Mainly we are going to focus on forward characteristics rather than reverse characteristics, just because in the forward characteristics it acts as a silicon controlled rectification. In reverse bias it just acts as a normal conventional diode. When I simulate this, let's look into that aspect. The x-axis parameter what I require is a VA. So in order to change that, what I require is I have to go to the settings, go to the x-axis, go to the axis variable. Then I have to find out especially this particular voltage or anode voltage. So I got a axis here 0 to 10 volts. I have already applied the variations here. Simulation edit profile. You can observe here. I have applied primary sweep is VAK, which is varied in this extent, and the secondary sweep is the gate voltage, which is applied in this start value is 0, end value is 5, and incremental is 0.1. The y-axis which is required is I require anode current, this one. This trace expression is written here and plotted here. You can observe now it is a little similar here. When IG is 0, you got something breakover voltage here. Then after when IG is increased, so immediately it turns on at the rapid stage. That is clearly shown over here. When IG is 0, this curve been observed. So this particular region is a breakover voltage. Then when IG is increased, so you are getting a different curve. This is well depicted here. In this way, we can understand the behavior of the silicon controlled rectifier. Thank you.